Good morning, everybody. Welcome to the announcement of the winners of the BattleDIM 2020, the Battle of the Leakage Detection and Isolation Methods. Today, we will start by a short presentation by my colleague, Dr. Stelios Vrachimis, who will present an outline of the competition. Next, we will announce the winners, and then we will present the top 5 online lectures from the winning teams, and we will close the presentation with some future steps. My name is Dimitris Iliadis. I'm a research assistant professor at the GEOS Research Innovation Center of Excellence of the University of Cyprus. Well, you can't see me on the screen, but I will give the floor now to my colleague, Stelios, who will make the first presentation.
Good morning, everyone, and welcome to the announcement of the winners of the Battle of the Leakage Detection and Isolation Methods 2020. I will share my screen so I can make a presentation about the battle. So I am Stelios Vrachimis. I'm with the GEOS Research and Innovation Center of Excellence. I'm a member of the BattleDIM Organizing Committee, and today I will present the problem design and evaluation of the results of this battle. First, I want to thank the Organizing Committee for helping organizing this battle, namely Dimitrios Iliadis, Ricardo Daormina, Avi Osfield, Zoran Kapelan, Marios Kyriakou, Pavlos Pavlou, Mengin Kiu, and Marios Polikarpou. But I want to especially thank Shuming Liu, the chair of the CCWI WDSA 2020 conference, who helped realize this battle, believed in this battle, and was willing to include it in the conference. Unfortunately, the conference did not take place, but hopefully we had a successful battle. I will begin with the description of this challenge, of the battle challenge, which concerns the L-Town, a water distribution network created based on a real network from a city in Cyprus. And this network covers an area of approximately 10,000 people. It has 42 kilometers of pipe length, 2.6 by 3 kilometers width, several junctions and pipes, and for the purposes of the competition, the pipe segments were divided into 50-meter segments. We have created the base demands of this network based on the real network. For each node, we assign the polygon in the real network, and we find the building area in this polygon from the real network. We then find the type of consumers by collaborating with the water utility for each building, and the base demand for each node is calculated by multiplying the percentage of this consumer type in the polygon times the consumption per building area of the consumer type times the building area. The demand patterns were also created realistically based on the real network. First, we created 2 nominal patterns, a residential and a commercial, extracted from real data. And however, each node was assigned a unique demand pattern by randomizing these nominal patterns as described in the LeakBusters benchmark, which is cited here. We also assigned some industrial patterns which were derived from real AMR data. The duration of the patterns was 2 years in 5-minute steps. We have a seasonal, yearly, and a weekly component periodicity. We also took into account the peaking factor, which is the maximum daily demand with respect to the average daily demand, so that it matches the system size. For this competition, we did not assign any special days in the patterns. The network exhibits different pressure areas, and as we can see in the pressure map on the right, the normal pressure during fault-free operation is between 2.5 to 6 bars. The tank was designed to fill during the night and release water during the day. Also, we solved the hydraulics of the network using pressure-driven demands, which were solved using the water network tool for resilience or winter. For the competition, we had a nominal model and a real network model. The real network was used for generating the data for the competition. The nominal model, given to participants as an EBANET input file, contains the available network information. The differences of the two models is that in the real model, the base demands were randomized uniformly between plus minus 10% of the real value. The demand patterns, the nominal, residential, and commercial patterns were available only on the nominal model. However, as we said, different patterns for each node were used in the real network, and also industrial patterns were not available. However, they are measured by AMRs. The pipe parameters again were randomized uniformly between plus minus 10% of the real value. For this competition, elevation and pump care uncertainty were omitted to reduce problem complexity. We have also included topological uncertainty in the real network. That is, we have pipe 37 and 251 closed in the real network, whereas in the model they were shown as open. Here we can see the closed pipes in the network. The sensors assigned in this problem was one water level sensor at the tank, 3 flow sensors, 1 at the pump and 2 at the DMA entrances, and 33 pressure sensors shown in the figure here, which were placed using a sensitivity matrix method. We have also 82 automatic meter reading devices in area C, which were used to measure this area, and also the industrial consumers shown here in green. The sensors give accurate readings with no time delay in order to reduce problem complexity. However, the readings were rounded to 2 decimal points, so this was adding some uncertainty into the measurements. We have 2 datasets, the historical dataset of 2018, which contains 1 year of sensor data, and also the time and repair location of pipe bursts that have been fixed by the water utility. The evaluation dataset, the one on which the participants were evaluated on, contains only 1 year of sensor data. We now continue to the objective of this competition, which is finding the leakages. The leakages in this competition were assumed the only fault that exists in L town, and this includes both pipe burst as well as background leakages. The modeling of the leakages uses a pressure-driven model as described by Crowley and Luvar in the reference here, and the parameters of this equation were chosen as shown here. We also assigned different discharge exponent coefficients for steel pipes and plastic pipes in the network, which were distinguished by their roughness coefficients. There were 3 types of leakages categorized depending on their magnitude in the competition: background leakages, medium pipe bursts, and large pipe bursts. These were categorized based on their percentage of the average system inflow. Large and medium leakages, that is above 15 cubic meters per hour, were assumed to be detected and fixed by the water utility after a reasonable amount of time, with a maximum of 2 months. Leakages was also assigned a time profile. There were abrupt leakages that begin abruptly and remain at their maximum whole hole value, but there are also incipient leakages, which increase gradually from their start time until a peak time, at which point they remain at the leak hole remains at its maximum value until the end of the leakage. For this competition, we used also a leakage placement algorithm, which places the leakages randomly, however, with some constraints. We place them constrained on the maximum number of leakages in a year, and also a minimum time between leakages which overlap. The leakages which overlap, meaning that the detection radius around the leak, which is from where the detection is considered successful, is 300 meters in this competition, and we assigned a minimum 2 weeks between leakages that overlap. This is to ensure separability of the faults. Leakage characteristics were also selected randomly with constraints. That is, we have predetermined number of background, medium, and large leakages, predetermined number of abrupt and incipient leakages, where incipient peak time is selected based on the leakage type and magnitude. We now proceed to the leakage locations. This is the leakages in the historical dataset. In total, there are 14 leakages in the historical dataset. 10 of these leakages were fixed by the water utility, and this information was given to participants. 4 background leakages, however, were not fixed and continue into the 2019 evaluation dataset. In this graph, we can see the evolution of the leakages in the historical dataset. We can see that they are spread around the year and that it comprises mostly of large leakages, except the 4 background leakages which continue until the end of the dataset and into 2019. Now we proceed to the evaluation dataset leakage locations. These are the leakages and the solution of the BattleDIM competition. There were 23 leakages in total. 4 begin and continue from 2018, while 19 of them begin in 2019. All these leakages are evaluated in this competition, whether they begin in 2018 or 2019. In the next graph, we show the evolution of these leakages. We have leakages of different size, background leaks. 3 of them begin in 2019 and 4 of them continue from 2018. We have 10 medium pipe bursts, 6 large pipe bursts, and also the time profile of these leakages vary. There are 10 incipient leakages, 9 abrupt leakages, and 4 continuing from 2018. So they are continuous. We now proceed to the evaluation methodology. For this competition, we follow a pure economic approach for evaluation of the participants. That is, the water utility of L Town calculates the profit from water saved from successful detections. Also, the utility considers the cost of the repair crew every time it is sent to search for a leakage. We want to note that the selected methodology was chosen by the organizing committee as the most suitable for this competition. However, alternative methodologies have also been considered and will be described in a future journal paper. A set of rules will apply to the results given by the participants to calculate the score. First, we define the true detection or true positive condition. And the true detection is a detection pointing at the time during the lifetime of a leakage and within a predefined pipe length distance from the leak location. A false detection is a detection which does not satisfy condition 1. Missed detections are the leakages in the 2019 dataset which have not been detected. The detections are evaluated in a chronological order. That is, from the earliest detection until the latest detection is given, and this is for the leakages that may overlap. Detections outside the 2019 are ignored, so we do not penalize any detections that were given with a date that was noted in 2019. Also, repeated detections of the same leakage are ignored, as we have cases that for the same leak was detected multiple times. We only consider the first detection of this leak, and the rest of the detections were not penalized. A single detection may detect only one leakage, even if more than one leakage is the detection area. In the case of multiple detections, the only leakage closest to the detected leak is considered to be detected successfully. The profit from water saved from a detection is calculated by finding the volume of water saved from the detected leak, from the detection time until the end time of the leak. The volume of water saved is then multiplied by the cost of water per cubic meter to calculate the total profit per detection. Also, we calculate the utility repair cost for each detection. If a detection is not near a leak, then the full repair crew cost is assigned to that detection. While if a detection is close to the location of a leak, the utility repair crew cost decreases linearly with respect to the distance from the leak location. The score per detection is then given by adding the profit and the cost, and the total score for a given results file is calculated by adding all the scores per detection. Here we show the evaluation parameters for the BattleDIM. The max detection distance for a leak is 300 meters. That is a detection that is 300 meters in pipe length from the leak location is not considered successful. The cost per cubic meter of water was chosen to be 80 cents of euro. And this is the typical cost of water in Cyprus, since the benchmark we have used is created from a network in Cyprus. And also the maximum repair crew cost was set at 500 euros, which was also is also the typical repair crew cost for in Cyprus. On the right, we can see an example of the evaluation function using these parameters, and a detection which is given here is assigned the corresponding cost or reward depending on the leakage location and time. The evaluation code is available on GitHub, and everyone is invited to go into GitHub, download the scoring algorithm, and test their results file themselves. If you have problems with the required software, that is MATLAB and the EBANET MATLAB toolkit, you can also run the evaluation algorithm online using CodeOcean. However, this may take a few days because we are pending approval from CodeOcean. More code will be available shortly. We'll make available in GitHub the code for the generation of the BattleDIM network, the sensor placement code, and also the leakage placement code. Thank you for your attention. I will now pass on to my colleague, Dimitrios Iliadis, to announce the winners of the competition.
Thank you, Stelio. Let me just change now the slides. Okay, so I think you can see my screen now. So it's time to announce the competition winners of the BattleDIM 2020. Mute. So, first, a few words of acknowledgements to the funding agencies that partially sponsored this competition. Before I announce the winners, I want to say a few words. This was a journey with some obstacles, as you are all very well aware. Initially, we announced the competition on December 2019, when we announced it through the CCWI WDSA website, and also we released the 2018 historical dataset together with a new L-Town EPNet model, the benchmark. On January, we updated the network, and we also, based on the feedback that we got from users and to make it more realistic, and also we published the 2019 evaluation scale and dataset. Unfortunately, February and March was one of the most difficult periods for everybody. It was a pandemic. On February, we had the announcement that the CCWI WDSA conference was postponed, and the competition was also postponed. In March, in light, we knew that the competition was, we knew that the conference was going to be held in 2021. It was a very difficult period for everybody, but we decided that we need, the community really needs to have, let's say, a ray of hope and to be active. So we decided to organize BattleDIM despite the COVID-19 situation. I'm happy to say that everybody embraced this decision. So I'm really happy, and I would like to thank everybody for supporting us in this decision. So in June 2020, it was a deadline, the extended deadline for the submission of the detection and isolation report by all participants. Some statistics: almost 100 people downloaded the datasets, and in the end, 18 teams participated in the competition from practically everywhere, from a lot of countries around the world, from Brazil, China, Colombia, France, Germany, Italy, Korea, Netherlands, United Kingdom, USA, Saudi Arabia, Singapore, Spain, and maybe from other countries as well. So it was really an international competition. These are the teams. I would like to just briefly name them. Artesia team from Artesia Consulting, Cheng from a team comprised from KAUST and Harping Institute of Technology, CIA, CUA from Universidad de los Andes, Cubalytics from Germany, DNW from Kunming University of Science and Guangdong University of Technology in China, DHI China and DHI Singapore as well participated, Universidade Federal de Minas Gerais in Brazil, Universidad de Campinas in Brazil as well, Ingeniusware in Germany, Valencia University in Spain, Inference Labs from the from Imperial College London, IRI team from IRI in Spain, UPC, and IMT Lille and Douai, KU Hadro System from Korea University, LeakBusters from TU Berlin, NC, North Carolina State University, as well as the Einstein Center of Digital Future, Tongji team from Tongji University in China, Tsinghua team from Tsinghua University in China, Under Pressure from TU Delft in the Netherlands, 3S Consult in Germany, and INRAE in France, Unife from University of Ferrara, Bentley from the US, and also the University of Zhejiang in China. So again, a big thanks to all participants. We are all virtually applauding right now. but this is a very sincere and this competition will not be a success without all these participants. All the videos and the presentations are available on the website. So all participants were submitted an abstract, and also they submitted an online presentation, and you can find those on the BattleDIM website, which is also available on the chat. And also this presentation is going to be available on the website as well. So the top 5 winners, of course, in reverse order. We have 2 honorable mentions. That is the 4th and 5th position, and they go to Team Unife, comprised of Irini Marzola, Filippo Manzoni, Stefano Alvisi, and Marco Francini. Congratulations to the Unife team. The next honorable mention goes to Xiaoding Wang, Junyu Li, Jibeng Zhu, Zibing Ma, and Yujun Huang from Tsinghua team. Congratulations to the Tsinghua team for the honorable mention. So these are the 5th and 4th positions based on the ranking that we did. And now let's go to the 3rd place. 3rd place goes to the LeakBusters team. Congratulations to the LeakBusters team. It's comprised of Yvonne Daniel, George Pesandes, Simon Ledkus, Mohammed Ali Khazar Fazae, Faizil Al-Kami, Kumar Mahintha Kumar, Emily Berlang, and Andrea Cominola. I really apologize for the pronunciation, but congratulations to the LeakBusters team for achieving the 3rd place. And we don't have a 2nd place because, in fact, the committee decided that we had a tie. This is really an incredible result, but 2 teams managed to be so close that we could not distinguish between 1st and 2nd. So the committee decided to give for the 2 teams, for the remaining 2 teams, to share the 1st prize between those 2 teams. And the 1st place is shared between Team Under Pressure with Stephen Bauer, Deur, Lane, Gilbert, Piller, and Abraham. Team Under Pressure, congratulations to the team, and to the team Tonji team with Jirong Li and Kunlun Jin. Congratulations to the winners of the competition. This is the ranking. So just as you can see, both Tonji team and Under Pressure, they had the highest true positive scores, and also they had the highest economic scores. You can see that the economic score is extremely close, but also the one team had more true positive, managed to get more results than the other. So we were in a Pareto optimal solution. So that's why we decided to give to the 1st position to both teams. You can see that the maximum economic score that was achieved was 264,000 euros. And you can see the results with the other teams. all the other participants will be able to evaluate their scores using the tools that my colleague Stelios presented before. Now, let's proceed. Let's view. Let's watch the presentations of the five winning teams. The presentations are also available on YouTube. They will also be available on the project on the competition website, as well as on the conference website, in case somebody has trouble in watch them on YouTube. Now, please allow me to share the videos now. Just a moment. Share. I need to make some zoom adjustments and to share the video.
Hello everyone, we are a team from Tongji University. We are pleased to participate in this battle, and we are honored to have this opportunity to share our method of identifying leaks in L-Town. I'd like to divide our presentation into 4 parts: background, methodology, highlights, and case study. First, I will start with the background. The water distribution network is one of the most important infrastructures. However, due to many reasons such as poor quality pipes, aging facilities, and man-made destruction, pipelines are vulnerable to be damaged, resulting in energy waste and potential contamination. As shown in Figure 1, leakage is common to the WDN of many countries, and as we all know, leakage accounts for most of the non-revenue water. In this research, we proposed a novel multiple leak detection and isolation framework, MLDIF. It contains 3 parts: calibration, identification, and isolation. A data module is also acquired. First, a gradient iteration algorithm was used to calibrate the hydraulic model after dividing pipes into several groups by the Dijkstra algorithm. Then we used STL decomposition and k-means clustering algorithm to identify the occurrence time of leaks. After that, the approximate quantity of leakages can be obtained with the help of flow forecasting. In order to locate the leakage position accurately in the shortest time, we used a stepwise leakage localization method. The meaning of the symbols that appear afterwards is as follows. The first step is to construct the benchmark leakage dataset. After hydraulic simulations are carried out separately for cases with and without leakage, we got the node pressure for those cases. Using the pressure data, we can calculate the average reference vector of pressure difference by equation 1. The second step is to narrow the area of possible leakages. The average actual leak signature can be calculated by equation 2. The similarity between delta P and delta P star is decided by the cosine distance between them. Only the pipes with the cosine distance greater than the reliable distance are considered to have the risk of breakage and need real-time leakage simulation. In the last step, we performed hydraulic simulation for cases when the real-time leakage happens on each pipe obtained in step 2. The quantity of leakage can be estimated in the identification part. Then the hydraulic feature of pipe leakage at every time step can be computed by equation 3, while the feature of real leakage can be obtained by equation 4. By ranking the average Euclidean distance between delta S and delta S star, the most likely leaky pipe can be figured out. Compared with other leakage identification methods, MLDIF has 4 improvements. First, it can effectively distinguish WDN's operating conditions with the help of the STL decomposition and k-means clustering algorithm. And it is insensitive to leakage size because the influence of the leakage size is removed after the normalization in equation 1 and 3. Therefore, this method is robust. Besides, due to the stepwise leakage localization and the search area narrowing step, MLDF can accurately locate the leaky pipe in a short time. Okay, now we move to the last part, case study. L-Town is a small hypothetical town and receiving water from two reservoirs. A pump and a water tank has been installed in the inlet of Area C, and most of its nodes are monitored by AMRs. Since the water supply in Area C is relatively independent, we can separate it from Area A and B and identify leakages respectively. According to the AMR records and the consumer types of the nodes in Area C, we can calculate the annual change of water consumption of each type. Then, with the help of the consumer types and base amount of nodes in the EPNet model, the total water consumption of each area can be predicted. According to Figure 8, it can be estimated that there was almost no leakage in early 2018. Therefore, pipe roughness is considered to be the main parameter that needs to be calibrated. After calibration, the predicted pressure value is better fitted to the observed value at nodes with pressure sensor. With the well-calibrated model, we can simulate the leak-free conditions throughout the year, and combined with the measured data, we can calculate changes of pressure difference during the year. Then the STL is used to decompose the time series into seasonal, trend, and residual components. Since the residual component cannot effectively reflect the incipient type of leak, we determined different leak conditions by clustering the trend part to different groups. The changes in LCI means the changes of the leak state. Take the marked time period as an example. Combined with the water volume difference diagram, the amount of the leakage can be roughly estimated to be 28 cubic meters per hour, and the time range of leakage can be identified. Hydraulic simulation was carried out for this period, and the SPC method is used to accurately get the time when the leakage occurs. By performing the similar analysis on the different leakage states throughout 2019, the start time of all the leakages can be obtained. Now we come to the isolation part. In order to compare with the existing leak report, we take the leakage that occurred at pipe 158 on October 6, 2018 as an example. First, the constructed leakage characteristics are used to narrow the range of possible leaky pipes. Then real-time simulation helps to get the most likely leaky pipes in 20 seconds. The topological distance from the pipe with the highest probability to pipe 158 is only 1, which is very small, and it proves the accuracy, efficiency, and good applicability of MLDF. The distance between the leak signature of the 20 pipes in the right figure and the real leakage features is shown in Figure 16. When locating the new leakage in the next period, if the current leakage has not been repaired, this leakage should be added to the hydraulic model to construct a new, quote, leak-free model. Through the above method, the identification of multiple leaks is realized, and all detected leakages are shown in this picture. This is the reference. If you have any questions, please feel free to contact us, and here are our email address. That's all. Thank you.
Hello and welcome everybody to our contribution to the BattleDIM 2020, the battle of the leakage detection and isolation methods. My name is David Steffelbauer and I'm a Marie Curie Fellow at the Water Management Department at TU Delft. This work is a joint effort between me, Jochen Teuerlein from 3S Consult from Karlsruhe, Denis Gilbert and Olivier Biller from INRE, Bordeaux in France, and Ido Abraham also from TU Delft. The 5 of us together built the team under pressure. To solve the leakage problem of the L-Town water utility, we have proposed a hierarchical approach to find the leaks in the 3 measurement zones. This presentation follows exactly this approach. First, we will start with the calibration of the network, both for demand and for roughness. Then I will introduce the foundation of our work, the dual model approach, which makes finding leaks tremendously easier. Last but not least, I will give an overview of our methods to detect and to localize leaks, which are both based on the dual modeling approach. Let us start with the demand calibration. We focused on the AMRC measurement zone C of the network and used time series analysis to identify the water usage behavior in L-town. The idea is to subsequently infer the demand to unmeasured nodes in zone A and B according to the information from the previous water bills, which is contained in the EPANet input file. The zone contains residential, commercial, and industrial consumers. We use time series analysis to derive general demand patterns for the commercial and the residential consumers. The best model for both user groups has been a multiplicative time series model consisting of a trend, T, a weekly seasonality, S, and a random noise component, R. At the bottom of this slide, you can see on the left side the trend over the year for the residential and the commercial users, and on the right side the seasonal component that repeats every week. It has to be noted that the industrial users follow the same model, although with different seasonal periods, which repeat with prime numbers all 7, 11, or 13 days. Since there are no industrial users in zone A and B, we were only interested in residential and commercial demand patterns. We stated the roughness calibration as a weighted least squares problem with bound constraints, which was solved with the help of Levenberg-Marquardt algorithm. We grouped the pipes into 6 groups, one belonging to measurement zone B, one to C, and the remaining 4 groups were divided according to their diameters and original Hazen-Williams coefficients, according to the EPANet input file. On the right side of this slide, you can see the convergence of the roughness parameters. Additionally, our method allows to compute confidence intervals for the roughness parameters based on first-order second moments. All groups resulted in very certain and reasonable roughness values. Group 1 and 5 show bigger confidence intervals due to their small number of pipes and the fact that they are hydraulically not that influential in the system. Now we get to the core of our idea to detect and isolate leaks, the dual model. In the dual model, the original pressure measurement nodes are connected by a valve with the virtual reservoirs. The origin of the name dual stems from the fact that instead of using a fixed demand boundary condition, the dual fixed heads are used. The heads of the reservoirs are set equal to the pressure measurements. If a new leak appears in the system, the residuals between measured and calculated pressures are increasing. The pressure drop caused by higher flow velocities towards the leak in a real system is not observed in the model that is still based on the leak-free system. In the dual approach, the measured pressure drop is applied to the fixed head reservoirs, and as a consequence, an additional outflow is calculated. This outflow can be understood as outflow residual. The advantage of the dual method is that the calculated outflows act as an amplifiers that deliver significant and localized signals even for small pressure drops. In addition, the outflows at the virtual reservoirs are a good first estimate for the leak size and location, as you can see on the right side. For the leak detection, we make use of the dual model outputs, the virtual leak flows. As mentioned before, the leak signals are amplified by the dual model, whereas the noise levels are way smaller than using the original pressure and flow measurements. The virtual leak flows show 2 different types of leaks that occurred in the system: instant leaks and growing leaks that saturate at a certain level, both shown on the left side. For the growing leaks, the increase over time was modeled with a quadratic function. We used change point detection algorithms like QZoom and the likelihood ratio method to retrieve first estimates for the leak start times. The input parameters of the algorithms were calibrated on small noise levels that were still remaining in the virtual leak flows. To retrieve even better start time estimates for the battle, we made use of Bayesian inference for single occurring leaks, which used all flow and pressure measurement signals as input parameters to fit the identified leak shapes on the measured signals. With this method, we were able not only to retrieve confidence boundaries for the start times, but also simultaneously probabilities for the leak size as well as the pressure drops in the system. If multiple leaks occurred at the same time in the system, this method had difficulties to find the right parameters. That is why we fell back on a simple genetic algorithm in the case of simultaneous leaks. The virtual leak flows from the dual model were also used for finding leaks. The localization is based on the work of Perez et al., which used Pearson correlation coefficients between pressure residuals and sensitivity matrices. The difference in our method is that we are not using pressure residuals, but instead the residuals in the virtual leak flows, which makes the method way more stable and robust. On the right side you can see the fitness function values based on the correlations. The smaller the values, the lighter the colors of the pipes, the more likely a pipe is to be the actual leaky pipe. The last slide shows the results that we obtained with our method. In total, we have found 32 leaks, or in other words, 22 leaks additionally to the 10 leaks that were already identified by the L-Town water utility. On the right side, you can see the locations of the leaks, on the left side, when they happened in the system. 4 leaks were identified in Zone C, 2 in Zone B, and the remaining 26 leaks occurred in Zone A. The leak sizes vary between 1.33 and almost 10 liters per second. In total, the L-Town water utility has lost 665,000 cubic meters of water due to leaks in their system in the years 2018 and 2019. So, that was our short presentation, and I want to thank you all for your attention. If you have any questions, I'm happy to answer them via mail, or we can also meet virtually on Skype or Zoom.
Hello and greetings from Berlin. Here in Germany for the presentation of our part in the BattleDIM 2020. My name is Ivo Daniel from the Smart Water Networks Group at Technische Universität Berlin, and together with a group from the Department of Civil Construction and Environmental Engineering at the North Carolina State University, we developed a two-stage approach titled A High-Resolution Pressure-Driven Method for Leakage Identification and Localization in Water Distribution Networks. Throughout this presentation, I will first briefly introduce you to our team. Then I will elaborate on the methodology underlying to this work, followed by the presentation of the results, meaning the time and location of the leaks we found in the BattleDIM dataset, and also a very brief discussion.
So let's start with the introduction of our team. To tackle the challenge of the BattleDIM 2020, we decided to divide and conquer. The group from the Technische Universität Berlin focused their efforts primarily on the leakage identification part, whereas the group from the North Carolina State University focused their efforts primarily on the leakage localization part. Now, starting this off, I want to provide a general overview of the complete process with the following flowchart. In the first step, we obtain the time series of the raw data or the SCADA data from the pressure sensor readings in a water distribution network. This information serves as input for the leakage identification process and is used to build a linear regression model based on information from a normal state. The model is then applied to a state with a present leak and the reconstruction error is analyzed. From this analysis, we obtain information about the most affected pressure sensor, which is then passed to the leakage localization method. In a further step, the leak start time is determined, which is also passed as information to the localization method. Utilizing the information about the most affected sensor, the localization method provides, in a first step, the selection of several candidate pipes for the leak location. From these candidate pipes is then calculated, by successive linear approximation, the final location and magnitude of the leak. Now let's step into the details of each individual part. For the leakage identification process, we built a linear regression model based on the pressures of all available sensors. This model is calibrated in the first step for a time window where ideally no leaks are present. On the next two slides, I want to elaborate on how this linear model is possible and the derivation of the regression constants. The starting point to the regression is the Bernoulli principle as seen in equation 1, regarding energy levels at locations of sensor I and sensor J. As in this system, the pressure losses annotated for the respective nodes are calculated with respect to the supplying reservoir. From equation 1, isolating Pi and Pj yields equation 2. This can be transformed to the linear regression in equation 3, with the regression constant c reflecting the geodetic height difference between the nodes and the parameter m reflecting the relation of the respective pressure losses to nodes j and I. To analyze why this regression is possible, meaning why the expressions in equation 2 can be assumed constant, let's take a look at the term of the pressure loss divided by pressure for each node. In this term represented in equation 4, substituting the pressure at node I with the pressure loss relation of I and the reservoir yields the term on the right side. Now, assuming constant reservoir pressure and constant daily average pressure losses, the expressions in equation 2 can be equally assumed constant. In the second step, the model is applied to the time frame with leaks and the model error is analyzed. The first part of the analysis obtains the most affected sensor by the respective leak. Assuming that a leak occurs in the vicinity of sensor I rather than all other sensors J, the reconstruction error of these regression models will result positive, as the increase in pressure loss at node I that are caused by the leak is greater than the increase at all other nodes J. The information of the most affected sensor is then passed on as input to the leakage localization method. In the final step, regarding the current evolutionary stage of the method, the change point is detected by visual inspection. This analysis was very straightforward for pipe breaks, as they caused abrupt change points and clear mean shifts in the signal, whereas gradually increasing transient leaks do not show an abrupt change point, but rather a trend change, which was a lot harder to pinpoint in time. The information of the leak start time is then also passed on to the localization method as input. The leakage localization method was initially developed and published in 2017 by the NC State team, as shown in the reference on the bottom right. The basis of this method is the formulation of a minimization problem, which describes the pressure difference that occurs due to a leak in a linear form and relating it to the leakage magnitudes. The pressure difference caused by the leak is calculated with the observed pressure from the n number of sensors in the network and the simulated pressures for the same locations under no leak conditions. Initially, leaks are inserted into the system at a number of m candidate pipes, and subsequently the leakage magnitudes are optimized using successive linear approximation to minimize the L1 error. The first step in this process is to select the m number of candidate pipes where the leak might have occurred. As a starting point to the selection, the most affected sensor from the previous step is taken, and the pressure difference that was caused by the leak is calculated for all pipes and then sorted descendingly by magnitude. The top 50 from this list are selected for further consideration, where the reduction to a number of 50 was derived after analyzing the dataset from 2018. Finally, for reasons of computational effort, from the initial set of 50 candidates, a reduced set of 10 to 15 pipes is sampled to obtain the final m number of candidate pipes. In a second step, the final leak location for all candidate pipes are calculated by successive linear approximation using a combination of linear programming and mixed integer linear programming. The solution vector will contain leak magnitudes greater than 0 for all pipes where a leak is located. In case of a single leak, the location is obtained as the algorithm returns the solution vector with a single element different from 0. Now let's move on to the results. For the dataset provided for this competition, we detected and localized a total of 18 leaks. The list on the left provides a complete overview of all leak start times and respective locations as they were identified by our method. Most of these leaks were located in the bigger DMA-A of the LTAN network. One was found in the lower DMA-B and another 2 in the upper DMA-C. The timeline chart illustrates that all leaks were fairly spread throughout the year. In this chart, the red lines annotate bursts or pipe breaks, whereas the blue lines annotate transients or progressing leaks. The colors are transferable to the map on the right, where the locations of each leak can be spotted. To illustrate the functionality of the method, we provide the example of the first leak found in 2019. In the leakage identification step, the produced reconstruction error signal from the model is shown here. During the first period, until January 15th at 11 p.m., the signal is steady around the 0 line. After that, a clear mean shift can be observed, indicating a pipe break. The figure also indicates that the apparent leak was fixed on February 1st at 9:55 a.m. as the signal indicates that the network returns to its previous state. The leak start time at January 15th, 11 p.m. and the most affected sensor node at node 506 are then passed to the localization method. Starting from this information, the candidate pipes are selected as shown in the map on the right, which represents the bottom left corner of the LTAN network. From the candidate pipes, the SLA algorithm then indicates that the leak has occurred in pipe 114, marked in blue on the map. Finally, I want to move on to point out some of the challenges that we faced when applying our method along this competition. Firstly, during the process of leakage identification, unsteady supply pressure conditions in DMA-C due to the pump and tank operation rendered the application of the regression method unsuitable. Instead, we needed to fall back to analyzing the mass balance, which was possible as in DMA-C 82 out of the 92 nodes were equipped with AMR technology. Also, as we mostly rely on visual detection of leakage start times, smooth transients caused real difficulties, as the transient to the leak state was rather smooth. On the side of the leakage localization, the model error inflicted in the AppNet model is crucial to the accuracy of the algorithm, and the 10% error introduced for this competition already presented a challenge. Additionally, data for the seasonality of the demand was not available throughout the entire network, but was needed to calibrate the model. Therefore, the available data from DMA-C was extrapolated to adjust the demand of DMA-A and B. Better availability of the demand data would help in increasing the accuracy of the method. Lastly, the simulation optimization approach is computationally expensive, especially when needing to run for an entire year. This limits the level of detail in which the SLA algorithm can be applied. Specifically in this case, the number of candidate pipes needed to be sampled to achieve results in an acceptable amount of time.
So this presentation is coming to an end, and I want to use this opportunity to thank the organizers for the organization of this great battle and to thank my team for their great efforts. So thank you very much and goodbye.
Hello everyone, it's my honor to present our battle research in the conference. This is Tsinghua team from Tsinghua University. Our research topic is a multi-stage approach to detect and isolate multiple leakages in district metering areas in water distribution systems. Our presentation has 4 sections. First, let's see the background. As we all know, there are a lot of negative effects associated with leakages, and a lot of countries have regulations that request water utilities to detect leakages as soon as possible. One of the main problems that we face in leak detection is that we need to detect and isolate them really early. So, the main part of our research is how to reduce the time associated with detecting and isolating the leaks. Operating experience has shown that hydraulic model and district metering areas are useful to control leakage. Focus on the BattleDIM. The air-tongue network with hydraulic model and sensors are given in this battle. The challenge for air-tongue water utility is how to pre-detect special pipe leakages as fast as possible over time. In short, 3 questions need to be solved. First, how to extract the leak-induced signals. Second, how to identify the type of leaks. Third, how to localize the leaks. To address the problems, we developed a novel EILF method for multiple leakages detection. Let's see how the method detects leaks. The method consists of 3 steps. First, estimation of flow and pressure. Second, identification of abrupt and incipient leakages. Third, isolation of pipes with leakages. Let's see more details. As described in the air-tongue problem statement, the water utility has set up pressure and flow sensors at a few predefined locations in the network. Time series data collected from these sensors are provided. The variations in the pressure and flow data are caused by daily, weekly, and seasonal water usage patterns, leakages, and other uncertain factors. To facilitate the identification of leak-induced data from the time series, flow and pressure caused by the users are estimated by data-driven time series methods. It's assumed that the demand is composed of 10 items, periodic items, and random items. Then, we use empirical mode decomposition to extract the time series items. The EMD can decompose the original signal by subtracting the intrinsic model function successively. The trend items in demand mode can be represented by one of the IMFs. This trend item represents the annual change mode in water consumption in Area C or Area AB. Thus, the estimated value of water consumption in the Area AB can be calculated by equation 2, where QT represents the demand at node I, which is obtained through the hydraulic model. NAB represents the node set of region AB. As shown in the pictures, The blue lines is estimated values using our method. The gray line is the residuals between estimated and observed flow. For pressure estimation, the vector auto-regressive model is suitable for multivariate time series prediction. The periodic pattern of the original series is firstly removed and serves as the input of the VAR model. Then, we use the residual between the estimated value and the original series to identify the leakages. Because the leakages is an unpredictable event, the residuals will increase when a leak happens. Residual is still a time series with irregular fluctuations. In order to reduce the non-stationary of residual series, first difference and weekly difference are calculated to make the data smooth. The leaks are divided into two types, abrupt and incipient. The abrupt leaks are identified through different transformation. 3 sigma SVC limit is used to identify the sudden increase and decrease of the flow curve. Therefore, we can obtain the size, start time, and the end time of leaks. There is one more thing to figure out. How does this start time matches the end time? The equality of the variation of the flow is used to match the same leak. A complementary method to address this problem is to sort the pressure nodes residuals. For incipient leakages, a window size-based SVC slope method is employed to identify the incipient increase in flow residuals. For localization, we use the idea of control variates to localize each leakage for area AB. We find 2 weeks, one with the leak and the other without the leak. Then, making a difference between the observed pressure data at the corresponding time in the 2 weeks. Grid searching is conducted for nodes and emitter coefficient in EPANet simulation, and calculate difference between the simulation pressure results as before. Finally, MAC of 2 differences is used as evaluation function for this problem. We could find high probability area of leakage with low MAC value. Now, let's see the detection performance of this EILF method. Through difference transformation, the abrupt increase and decrease are easily identified by 3 sigma SVC method. Besides, we sort the pressure nodes residuals, as shown in the second figure. A sudden increase in pressure will lead to an increase in the residual between the current value and its moving average. The variation of the pressure at the neighboring nodes will be higher than more distant nodes. The birth and fix of a certain leakage will cause similar patterns for the neighbor nodes and the distant nodes. By observing the pattern at each start time and end time, a matching could be done. Therefore, 9 abrupt leaks are detected in the BattleDIM networks in 2019. For incipient leakages, as shown in the tables, 7 incipient leakages are identified by window size-based SVC slope method. However, the peak of each unfixed incipient leakages is hard to be determined because of the overlap of different incipient leakage. Therefore, an approximate peak time is given for each incipient leakage. For localization, the shade in gray represents the size of the MSE. The pipe with darker color has smaller MSE. Among them, red, orange, yellow, green, and blue indicate the 5 pipes with the smallest MSE. That is, the area with the highest probability of leakage. By using our EILF method, 16 leakages are detected and localized in the BattleDIM networks in 2019. Otherwise, 2 unknown leakages are detected and localized in 2018. Now, let's conclude with some highlights of the methods. Applying the EMD and VAR, accurate estimations of flow and pressure under normal conditions are used to extract link-induced values from the monitoring data. Rather than analyzing original pressure and flow signals directly, this study extracts key burst characteristics, reduces the impact of diurnal variations, and provided a better solution for leak detection. Second, weekly difference is calculated to reduce the non-stationary of residual series, which is used for leak detection. We also use the weekly difference idea to design the objective function for localization searching problem. This approach improves the ability to deal with uncertainty. Third, the equality of the variation of the flow residuals and the sorting of pressure nodes are used to match the start time and the end time of an abrupt leakage. Meanwhile, the window size slope variation method is proposed to detect the incipient leak start time and size. The EILF method provides an effective multiple overlapping leaks detection framework. Finally, results show that 16 leakages are detected and localized in 2019, which demonstrates the effectiveness of the solution from leak detection and localization in water distribution systems. That's all. Thank you for your attention.
Good morning to all of you. We are Irene Marsola and Filippo Mazzoni, PhD students from the University of Ferrara in Italy, and we are going to present our work for the battle of the leakage detection and isolation methods developed in collaboration with Professor Stefano Alvisi and Marco Franchini from the same university. Several approaches for leakage detection have been introduced in the last decades, differing in terms of data collected in field and the adopted numerical approach. We developed a methodology which includes the use of pressure and flow data and consists of a pragmatic approach based on the use of hydraulic simulation model and the comparison between simulated and observed data. In particular, the method consists of two phases. In a first phase, the model is calibrated in order to realistically represent the behavior of the network. This was a fundamental step to have at disposal a reliable tool for leakage identification. In a second phase, leakage start time and location are characterized. For each of these phases, a specific subset of pressure and flow data time series is considered. Concerning the L-town dataset, the two periods for model calibration and leakage identification are represented by year 2018 and 2019 respectively. As far as regards the model calibration phase, a first step included the evaluation of the demand seasonal variation, that is, the adjustment of the average weekly demands provided in the model. From an operational standpoint, a set of seasonal multipliers were evaluated for the L-town network by analyzing the demand data smart metered in a part of the network. The result of the demand adjustment operation showed the highest demand between June and August, in accordance with the fact that the network is located in the northern hemisphere. The second step included the obtainment of the leakage time series for year 2018 and the identification of the periods without leakages or including the ones reported in the 2018 leakage report. These periods were then used for hydraulic simulations, and the resulting pressure and inflows were compared against the observed ones. The differences between simulated and observed data were then minimized by adjusting pipe roughness and diameter in order to calibrate the model. Operatively, we used the dynamic link libraries of EPANET version 2.2 applied to the MATLAB programming software to perform the hydraulic simulations. We would like to remark that these two steps of demand adjustment and model calibration were a fundamental prerequisite for the subsequent operation of leakage identification and required the majority of the time for the application of the methodology.
The model calibrated with 2018 data was then used to detect year 2019 leakages in time and space. Specifically, regarding the number of leakages and their start time, the L-town leakage time series was obtained. The engineering judgment was then used in order to identify the time of leakage formation and repair. This was done by considering the main positive and negative variations in the leakage time series. In addition, a time interval in which each leakage kept steady or gradually increased was visually identified. Given the leakage occurrence period, the spatial localization phase was led through an enumerative approach by using the calibrated model. In particular, for each leakage, half of its entity was assigned to the two adjacent nodes of each pipe in turn, and an error was evaluated as shown in the reported expression. The leakage was then assigned to the pipe reporting the minimum value of the error. The above process was adopted to temporally and spatially identify each leakage affecting the L-Town network in year 2019. It is worth noting that the leakage history was built gradually and iteratively, sometimes by also considering the pipelines adjacent to the optimal one. Several scenarios were then considered, and the history related to the global lowest error was selected in conclusion. The method allowed to identify a total of 14 leakages. 11 leakages were found in Area A, 1 was found in Area B, and the remaining 2 were observed in Area C. To sum up, a pragmatic approach for leakage detection in space and time was introduced and applied to identify the leakages affecting the water distribution network of L-Town. The approach is simple and transparent, and it allowed to identify the leakage history only by relying on pressure and inflow data observed at each sensor and the iterative use of the hydraulic simulation model. However, it is worth highlighting that the performance of the method depends on an accurate estimation of the water demand in the network. In addition, since observed and simulated pressure are here compared, a well-calibrated model is essential to avoid leakage misclassification. Thanks to all of you for the attention.
So again, I would like to congratulate all the winners, and let's all give a virtual applause to the winners. Unfortunately, through Zoom, this is not through online. Through these online meetings, it's very difficult to communicate our how happy we are, but we would like to share our feelings of and the celebration of the success. So all the winning teams will receive a signed certificate for their success. So what are the next steps? So we invite all the participants to score their solutions using the scoring algorithm provided online to see how well they did. They will get a score similar to the ones in the same way as the scores that we showed, and you will be able to compare your solution with the other solutions. This is also for reproducibility. This is very important for research to be able to reproduce, to provide a mechanism so that we can generate data and reproduce our research results. Next, the committee will invite participants of the competition to express their interest in preparing and joint journal paper. This is going to happen in the following months. In the meantime, and in light that the CCWI and WDSA 2020 conference is postponed for 2021, sometime in September or October next year, that is, we invite everybody to send your abstracts to start preparing for the next battle. And we hope to see everybody in CCW WDSA next year in China. Thank you. Thanks everybody for the attendance, for staying up until the end. all the winners. And again, congratulations to everybody. This is the end of the BattleDIM 2020 competition, and we bid you farewell.